Hello, we're the Soft Robotics group, and this is our BME 644 final presentation.
Our select paper topic is a wearable cardiac ultrasound imager. It's presented by Yuanhao.
I'm Tian.
I'm Josh.
I'm Jonathan Lau. The paper that we have chosen is called a wearable cardiac ultrasound imager, and it explores the creation of a new ultrasound patch which can be used to image the heart. We will explore this paper more in depth later. We chose this paper for a couple of reasons. The first, that it was a recently published paper, meaning that it showcases the forefront of the newest technology. Additionally, many of our group members wanted to learn more about how we can use novel imaging techniques to improve current methods. Additionally, due to its novelty, it has a lot of implications that can lead to a lot of new advancements in the application of ultrasound in medicine. The most interesting part of this paper was its mix of novel materials, new fabrication methods, and its implementations of deep learning. All of these are reasons why we chose to use this paper to delve further into. All authors of this paper are current members of the Zhao Research Group in the Department of Nanoengineering at the University of California, San Diego. The first author on this paper is Hongjie Hu, who is a current postdoctoral researcher at UCSD. He currently has 11 publications according to Google Scholar and received his PhD from UCSD. His research interests include wearable technologies and ultrasound. Another contributing author is Xiaoxiang Gao, who is a current postdoctoral researcher at UCSD as well. He currently has 9 publications according to Google Scholar and received his PhD in acoustics from Nanjing University. His research interests include soft electronics, ultrasound, and photoacoustics. The PI and the corresponding author for this paper is Dr. Shen Xu. He is currently an associate professor in nanoengineering at UCSD. He is a highly accomplished scholar with over 41 publications according to Google Scholar. Additionally, he was awarded the IUPAC Prize for Young Chemists in 2011 for his PhD thesis. His research interests include novel materials for soft electronics for energy harvesting and storage devices.
Ultrasound imaging has come a long way since its early beginnings. It all started in the 1940s when Australian physics called first attempt using ultrasound for medical imaging, but it was in the 1950s that the field took a leap forward thanks to Swedish engineer Elder. He developed echocardiography, a technology that used ultrasound to image the heart. In the 1960s, real-time beam mode ultrasound was introduced, allowing for continuous imaging and motion detection. The 1970s saw another breakthrough with Doppler ultrasound, which enabled the visualization of blood flow in vessels and within the heart. And in the 1990s, marked the arrival of the 3D and 4D ultrasound imaging, offering improved spatial resolution and real-time imaging. Finally, from the 2000 to 2010s, portable and handheld ultrasound devices became increasingly prevalent, making this powerful diagnostic tool more accessible and affordable for medical professions worldwide. And that's a brief history of ultrasound from its humble beginnings to the advanced life-saving technology it is today. Next, we're gonna talk about why this is important to get hard, clear image. First and foremost, a clear image allows doctors to identify abnormalities in the heart structure and function, such as blockages, clots, or valley problems, and may lead to serious health issues. By providing a high-resolution view of the heart, doctor can make an accurate diagnosis of heart conditions. Second, this imaging technology assists physicians in determining the severity of the disease, planning treatment options, and monitoring the progress of patients' conditions. And third, by offering an accurate view of the heart structure and function, doctor can tailor treatments to the patient's specific needs. This results in improved treatment outcomes and faster recovery times.
So, some facts from the CDC. Heart disease is the leading cause of death for men and women in the United States. One person every 34 seconds died due to a cardiovascular disease. On the graphic on the right, we see heart disease death rates from 2018 to 2020 across the United States. This graphic demonstrates the prevalency of heart disease in the United States and its growth over time. Another sad thing is that many of these deaths can be prevented by early detection methods like echocardiograms or other forms of cardiovascular imaging. So these facts combined demonstrate the physiological and clinical need for the development of medical imaging devices, much like the one demonstrated in this paper. Another physiological limitation that many medical imaging devices have is that they cannot actively measure cardiovascular states. We're going to get into this a little bit more later, but I wanted to bring it up because though we can measure people's hearts before and after physical activity, it is really difficult to measure them during, and this information is really important when determining patients' overall health. Now, looking at current and competing technologies and their challenges, commonly used cardiovascular imaging devices, as shown on the left, generally consist of the following: X-rays and CTs, which utilize X-rays to develop back projection images, MRIs, which utilizes changes in magnetic fields to create images, and PETs, which utilize ingesting nuclear medicine in order to create imaging, and of course ultrasounds, which utilize sound. Now, many of these imaging modalities have their weaknesses. X-rays and CTs utilize X-rays, which can expose patients to radiation. MRIs can't be used if people have metal in them, and PETs overall have a weariness with patients. This means that ultrasounds are the ideal and because they provide high quality images while not exposing patients to potentially harmful radiation, and they're cheap and accessible for most people. However, the greatest challenge with all these devices is mobility. Patients must be still in order to be imaged, and that means that they can't be imaged when they're active, which uses a lot of data, as stated earlier.
Finally, we want to talk about the results summary and its impacts. Echocardiography is crucial in the diagnosis of the cardiac diseases, but the current implementation in clinics is cumbersome and limits its application in continuous monitoring. In this paper, the author provides a device that uses the scratchable patches, which provides the ultrasonic images, and the sensing mode is the biplane of 2D. Compared with the previous publications, the 1D and 2D, it provides the in vivo, real-time, and continuous sampling in motions images. By using machine learning techniques, it provides automatic image analysis. It has the 7 quantified functions, which means that the amount of the physiological signals collected from the images. For example, the number of the quantified functions in this work is 7 because they can extract the myocardium displacement, left ventricular internal diameter, fractional shortening, stroke volume, ejection fraction, cardiac output, and heart rate from those B-mode images. This work also has the great impacts. The device provides the uninterrupted frame-by-frame acquisitions of the cardiac images, even when the subject was undertaking intensive exercise. The wearable imager with deep learning gave actionable information by automatically and continuously outputting curves of the crucial cardiac metrics, such as the myocardial displacement, etc., which are highly desirable in critical care, cardiovascular disease management, and sports science. The implementations of this technology go far beyond imaging the heart, as it can be generalized to image other deep tissues, such as the inferior vena cava, abdominal aorta, spine, and liver. In below images, this is the B-mode images of the biopsy test on the commercial phantom, which we can clearly see the needle's position in the 2 orthogonal image sections. This is the video of the imaging-guided biopsy on the phantom by an orthogonal array. The 2 orthogonal image sections present the entire biopsy process simultaneously, freeing up one hand of the operator.
We would now like to talk about the limitations that we noticed in the paper and how we would improve upon them. The first thing that we noticed was the low sample size. If we were to do this paper, we would use a larger sample size with participants from different age groups, gender, and races, as well as health conditions, to get a better idea of the limitations of the sensor and if there's any inherent issues with the design. The next thing we'd like to improve is the manual needle tracking. We noticed in the supplementary information they did a test using needle tracking and they manually did that. we would suggest to use a machine learning algorithm to automatically track the needle insertion to make it easier and better.